So let's talk about a background theory of mass spectrometry before we start focusing on what we're going to eventually get to, which is quadrapole mass spectrometry or octupole mass spectrometry. So what is mass spectrometry? Well, the idea with mass spectrometry is that if we take our organic compound and we've got a whole front end here that separates it out from the others, but let's say we have a Witch's brew of compounds, we separate them out and we inject this compound and we want to analyze it. Well, what we're going to do is we're going to introduce a charge to this molecule. So we're going to put a positive charge on it. And the reason we're going to put positive charges on it is that we can make charges move. So if you subject a charged molecule to a magnetic field, it will move it one way or the other. It will move towards or away from the magnetic field. So first thing about mass spectrometry is how do you plan on ionizing? And there are what are called hard ionization and soft ionization methods. Soft ionization methods only impart a charge, and these are typically done through chemical ionization. So we would put something like, I don't know, sodium here. We would remove an electron somehow, and removing the electron will give the molecule a positive charge. Now, the advantage of this type of technique is that we only get the parent compound, that's it. So our only charged molecule is this molecule with a +1 charge. The downside is that chemical ionization tends to be a bit harder to do. So particularly if you're working with gas phase species like ethane or propane, it's not trivial to put a positive charge on that. We also have to find a compound that is very good at oxidizing this type of compound. So we need a strong oxidizing agent. So typically we work with hard ionization techniques, which are typically called electron ionization or EI. So what happens with electron ionization is that we inject our compound into a vacuum. And we have basically a glorified incandescent light bulb. There's a wire. We pass the current through it, and it ejects really high energy electrons. And these high energy electrons strike the molecule and they remove an electron. So it hits it, and we see this shoot off and this shoot off, and the whole molecule ends up having a +1 charge. Now, if that was all that happened, we'd have the same effect of chemical ionization. But the thing is that we hit it with such high energy electrons that not only does it ionize, it vibrates, and it vibrates so violently that it will begin to fall apart. So there is a second effect. Sometimes we do hit it too hard that we end up getting 2 ionizations +2. Don't worry about that. What we're really more concerned about here is that this is going to fall apart into fragments. One fragment's going to have a positive charge, one fragment's going to have no charge, because we can only have a +1 charge. Now, where that fragment is how it fragments depends on the stability of each of the functional groups. So we can clip it at the OH, we can clip it with the carboxylic acid, we can clip it at the ketone, we can clip it at the phenyl group or the C6H5 group. The thing is, we're going to end up with what's called a fragmentation pattern. So we may end up with something that looks like this, and this is the fragment that popped off of it. So there may be a positive charge in this ring, and when it snapped in half, we ended up with carbon here, or the charge could have been on the other one. The point is that we're going to have different fragments with different weights. Now, one of the things is going to be the parent compound with a positive charge, depending on how stable it is. But what we're going to do is we're going to take all these ions that we form, and we're going to funnel them in between 4 plates for a quadrapole. Now, as these ions go in, they have a positive charge. Some of them don't have any charges at all, they just kind of scatter off. But the ones with the positive charges, we're going to apply a DC current to 2 sets of plates. And these DC currents are going to create a constant force. Now, this molecule weighs a lot, it's not going to move that much. If it weighs too little, it's going to immediately fly into one of the plates and be gone. So this DC current here is going to basically select for our heavier elements, or our heavier fragments. We're also going to apply an AC current to the other 2 plates. So what the AC current is going to do is it's going to pull molecules in and out of plane with these 2 DC plates. As it does that, they're no longer affected by the DC plates. So this AC current is actually going to select for really light molecules because it's going to do a good job of pulling them out from between the DC plates, whereas the heavier ones, because the AC current can't move them that fast, are going to feel more of the effect. So we have an AC plates that select for light molecules, DC plates that select for heavy molecules. The sweet spot is where we're selecting for the same weight. So what we're looking for here is what's called the mass or M over Z, mass over charge or M over Z ratio. Now we're going to assume the charge here is +1, so it's going to be the mass divided by 1. By dialing in our AC and DC voltages, we'll start selecting for certain weights. And this is going to get us into how our mass spec actually begins to sort out and where we get the spectrum from to figure out the fragmentation patterns for mass spec.